Nice.
So today we're talking about RTK here and show you the video. Now there's a couple things here. I'm having a couple technical difficulties where I can't get rid of what you see what I see.
You're cutting in and out, David. I think I don't know.
This is a picture of me, much skinnier, much younger in 84. Can you hear me?
Yeah, I was thinking you were kind of cutting in and out, so I don't know if that was everybody or if it was just.
Maybe we had an interruption.
Go for it.
Anyway, back in 94, we purchased an Aztec RTK system that you see here, and that's me, much younger. And look at the size of the unit that we had then. We had the antenna on a 2-meter rod. That was a full backpack. Had a unit in there, a radio, so on and so forth. And we were tethered. There was no Bluetooth back then. And so the guy with the backpack and I had to stay within a few feet. It was the early RTK system. And that's how it goes. So we're going to go through a few terms, RTK and RTN. RTK, real-time kinematic. You have a base, you have an antenna, you have a known position, you're broadcasting from it. Generally, you're limited in distance by the radios that you use. And we used to use the old Pac Crest radios, and now most people are doing RTN, which is real-time network. And when you're using a real-time network, there are some limitations on distance, but it's not a mile or two. You could be out a long way and still get corrections, broadcast corrections. And that is important because you're dialing up, you're getting a solution, but you can get way out there. And why does that matter? It matters because of your parts per million. And I'm going to talk a little bit about the different sources of error and how RTK works. But in the simplest way, if you have a known point and you're bringing in GPS measurements to that known point, it's broadcasting corrections out to you on a rover. And so if you had a 10 by 10 and it takes a reading, it's taking what you get at the rover, broadcast those corrections, and it gives you a position. In its simplest form, that's RTK. Now, most people use RTK and RTN almost exclusively. And there's a lot of good uses for it. But if you're doing a LTA where you have a minimum detail survey where you have 750 parts per million, standards for urban, high urban, low urban surveys, then it's very important that you understand how the RTK works so that you know for a fact when you sign that certification that you are actually within that specification. And that's what we're going to talk about today. We're going to talk about what RTK actually is, accuracy-wise, and we're going to talk about how to check it yourself in the second half of the presentation. So the shorthand version, because I'm not going to teach error theory. That'll take a whole summer rod with an accurate bubble. It'd be an 8-minute bubble. So your typical, I'll start at the top. Your typical GPS is 1 centimeter, 2 parts per million. Some of them are 1 part, but 2 parts per million. 1 centimeter is 3/100. 3/100, when you read through the specification, that is standard deviation. What that means is 68% of your measurements will be within 1 centimeter. 3/100. 7 out of 10 is all you need to know. Okay, as surveyors, we are interested in 95% confidence. So that's times 2. So now you're 2 centimeters. So what that says is that 95% of your shots, 9 out of 10, will be 6/100. That's just the GPS unit. So 6/100, 95%. Now you have 2 parts per million. Here's how you figure your parts per million. It's 2 feet, because that's the unit, in a million feet. So when you're trying to figure out your parts per million, so then if you're a tenth of that, that means you're 2/10 at 100,000. Okay, that means you're 200ths at 10 miles. So if RTN base is further than 2 miles away, yes, Trent.
Yeah, you you kind of keep cutting in and out, so I think we're missing a few of the details as you.
Okay.
So
just raise your hand and I'll go back and I'll wait till our connection gets better.
Yeah.
So I was talking about parts per million. So parts per million is 2 feet in a million air. And so if you have 100,000 feet, it's 10% of a million. If you have 2 feet, 10% of that is 2/10. So now you go down to a 10% of that. In 10,000 feet, you have 200ths per million. Well, so if your base unit is more than 10,000 feet away, you're introducing more than 200ths. Now you already have 600ths, and now you're putting another 2 into the mix just at the head of the unit within itself. So the next thing is you have a 2-meter rod with an 8-minute bubble, which is the most accurate bubble most of our survey equipment has. So there's another 100th in your bubble. So as we do the math, and I show it here on the slide, about 900. Connection's good, Trent?
Start right there. Start now again.
Okay. Hopefully it'll improve.
Yeah.
Because I don't have any internet issues on here. I'm looking, but we'll work through it.
Yep.
So your RTK unit, if you're a couple miles away from your base and you put it together, you're at about 900ths at 95%. If you are measuring 2 points on a line, each 900ths, that means that you're within 1300ths on the line length. Now, if you're measuring a mile, 1300ths is fine. If you're measuring 100 feet, you have a problem. So that's the basics of what your RTK unit is. But what we're also going to talk about is that's 95% of the time you're within 900ths, all things considered. You would naturally think that that next 5% can only add 100th or 2. Well, that's not true. That 95% has a much longer lead on it. And I'm going to go through the math and show you how that works.
You want to, while you're doing that, you want to try, let's try turning your video off just and see if by not having your video on frees up some bandwidth for you.
I'm not sure how to do. Is it real choppy, Trent?
Yeah, it's pretty choppy. Try well, actually you're on the top now, so
let's turn the virtual camera off. Stand by.
Yep. Yeah, that'd be
okay. Can you hear me?
Yeah, we got you. We can hear you fine.
Can you see the slideshow?
And we still see the slideshow. We still see you too, but
I don't know what I got going here. Let's see. Okay, let's try it, and hopefully this will work out.
Okay.
So, and just raise your hand, Trent, if it gets wobbly, and maybe we'll try the connection. So, what I'm doing here is, if you look at the slideshow, this RTK accuracy by the book, I just walked you through it, and what I'm showing you here is a slideshow that Roger Frank did 15 years ago. And then I'm going to show you the new data. And the only difference between his data and my data is I was testing a GNSS system to see if I could yield better results. And I'm not going to walk through this spec because it's the same. So what brought this up in my local area is the county surveyor called me. The county surveyor called, said that they weren't fitting the tires. And the ties in our, okay, let's see what I can do.
Yeah. Yeah, we had no problems last time. It was good, but it's okay.
Yeah.
Is it on your left-hand side, your 3-cam with the Zoom call? I wonder if you're able to, on the left-hand side where it says scenes.
Oh, yeah. And I don't have that on.
Oh, okay.
See, yeah, that's, you see all 4, right?
Yes.
4 windows.
Yes.
This should be the minimum. Let's try it. And if I have to take a break, if we can't get it better, I'll make a technical call and see if there's something I can do.
Okay.
Let's see, start virtual camera. Okay, Trent, let's try it again.
Okay.
And for everybody, if this gets too bad, these are 2 videos on the 10-minute surveyor, both of them. So,
okay, perfect.
If you're using RTK and you're measuring 100 feet, you have a problem because you have 1300ths between those 2 lines. And a lot of precise measurement can't absorb that kind of error. That's like a 1 in 900 as opposed to a 1 in 10,000 precision. And so if you're measuring long lines, then you can absorb the error of an RTK unit, but it's something to think about. And as I was saying earlier, our county surveyor called and they were telling me they're having trouble with tie distances submitted by other surveyors. And they couldn't figure out, they went out and checked them and they were missing them by quite a little, new ties, over 1/10. And they called me and they said, what do you think's going on? And I said, I know what they're doing. They're RTKing them. They're RTNing them. And they said, some are within a couple hundredths, some we have more than 1/10. And I said, that's the deal. Call the surveyor and ask him how he measured it. And sure enough, he was using RTK, RTN. Our ties here in Southern California for centerline street intersections, what we do is we set lead back and tags in curves. You can always reestablish it using the ties. But if those ties have 1/10 or floating around, it destroys the quality of that tie. They should generally be within about 100th. If you're chaining them, you could for sure can get them within 100th. If you're shooting them with an instrument, you'll be within 100th. And so people are doing this. And I think it comes from a lack of understanding of how the RTK works. This is these are northings and they're tracking, and your mean is this black line right here. And each one of these are 1 second epochs. And these are measurements of how the RTN works over 15 minutes. So from the beginning of the slide, right here, if you can see my arrow, to here, it's 15 minutes. And when you look at my min, which is actually here, and you look at my max, I have 1700ths in my northings from min to max over 15 minutes. If I go to the easting, and this is how it works, and you'll see that it spikes and it'll roll through a cycle, several cycles. And the real danger is people say, I don't really care about my accuracy in my state plane coordinate. What I really want is relative accuracy, meaning from one point to the next. If I measure 2 XYs, I go out and measure the next 2 a minute later or 30 seconds later, the XY between those 2 is accurate, maybe not on a state plane system. Well, the northing and the easting are two different products and they're not correlated. I'll give you an example. You see how I start out here and my northing's climbing and it hits a peak here at about 217 and it hits a low here at 757. Those are seconds. Go to the next slide and look at this. Look how where my baseline is. You see how my eastings start out below my average. Then they get up here, but see 217, if I go here, they're coming down. So what that means is they're not correlated and they're not rolling together. So from one point to the next, you're not good relatively. It's not that you're not good, but you have an inaccuracy because XY measured now, XY measured 2 minutes from now, they're not relative because my easting might be detached and because it's not correlated to my northing, it causes an XY problem. And throughout the day, this is what happens is I have 1600ths min to max, 1600ths min to max in the northing. So if you do an XY, you have about 2500ths. Let's see, 10 by 10 is 1414. So it gives you, your 2600ths. So can your project absorb in a 15-minute span a 2500ths XY? I don't know. I mean, that's what you need to ask yourself. That's point to point. In the absence of that, you're within about 1300s. And I don't want to get too wonkish. This is just give you a sense of what you have. And that fits right in there with the 1300s that we had earlier. This is showing you 16, 13 min max because that includes all measurements in 15 minutes. So now this is the troubling part, elevation. And we know that we have 1 centimeter in our in our horizontal with RTK. We have 2 centimeters. So if I have 900ths in a standard RT12, I have close to 1200ths in my vertical. Oh, look at that. Internet connection is unstable. There's my issue. It's raining here. I don't know if that matters. We'll work through it. Here's the important thing to pick up on this slide is my min, which is my minimum measurement, to my maximum, my delta in my vertical is 4200ths. So if you're out doing something with an RTK, you have a couple tenths, potentially all shots considered horizontally, and you could have up to 4 or 5 tenths in your vertical over 15 minutes. Well, you're not working 15 minutes. You're working for 6 or 8 hours. And over those 6 or 8 hours, it's going to cycle exactly like this. And that's important to understand how it works. I'm going to step through. This was some old data. So what I did is I took a GNSS away from a CGPS or CORS station. So in my CGPS station, what I have here is no PPM because I'm right on top of my base station. I'm collecting data at 1 second and I collect it for about 3 hours. And this was my test. And I was on the roof of a building, so I had no obstructions. So what did I find? And it says, go to my Excel sheet. So let me go to my Excel sheet. Let's see what the next slide is. Yeah, there we go.
Good advice on that next slide coming.
Yeah. And you can see this Excel fine,
Yes.
Trent?
Yep.
Can you see this Excel? Okay, great.
Yeah, we're seeing it.
What I have here are northing, easting elevations collected at 1 second epochs, and I have over 10,000 measurements. So in doing my 10,000 measurements, here's what I found. I hit that GPS spec per the, I hit the GPS spec per the instrument. Nope. Not hearing me, Trent?
Yeah. It's
Okay.
in and out. Yeah, it's in and out.
Yeah, I know it's tough to hear. Let me just check my cell connection. Yeah, see, I have like 5 bars here.
Yeah.
So
Okay.
we'll just have to work through it.
Yep.
Dave, can you zoom into the area on your spreadsheet that you're showing?
Yes.
Thank you. It's hell getting old.
And when I go through 10,000 shots, about 3 hours and 15 minutes of data, what I find is that I hit the manufacturer's specifications of 300, 1 centimeter. And of course, you know, I will, or I should, if I have a large enough sample set, because your manufacturers have an interest in making the most accurate equipment and advertising it as they can. So if they say 1 centimeter, those are in optimum conditions, what I would presume to be millions and millions of measurements, because that manufacturer has to test this equipment and advertise it accordingly. And so you don't need to do this test to know what your answers are going to be, because the manufacturer tells you. But what they don't always tell you is that 1 centimeter is 68% standard deviation. Times 2 is what they leave out, 95%, 2 centimeters. And they don't give you a handy diagram telling you what parts per million are, or all the other sources of error. We don't need that because we're land surveyors. So when I go through all the data, I am within 300ths by 300ths. And for whatever reason, I had 900ths in my vertical, but that's fine. So going through this data, I'll show you what a graph's like. This is a graph of 1 second data. And to show you where we are in this, I'll zoom in a little bit. Stand by. And I'm going to show you how to do this before the end of the presentation, because you can test your own right out in the parking lot. If I get on this data, now, there we go. So if I pick a point, it shows me at 7 minutes, 35 seconds into this data, I have a northing of, let's just say 2.5, reading the last 3 numbers. That's at 7:35. Here at 13 minutes, so about 6 minutes later, I have a 2.4. So I have a 10th in those minutes. And you can chase this out. So this is at 13 minutes. I have a 2.4, 2.39. At 14 minutes, almost 2 minutes less, now I have a 2.53. I have 14 hundredths in less than 2 minutes later. That's how your RTK measures. I come back over, I grab one here. Let's see the live data. At 28 minutes, I have 2.5, 2.53. And 3 minutes later, I have a 2.4. I'm cycling 1300s. Does that sound familiar? I should be 95% of the time. And you remember when you're looking at 600s, it's plus or minus. And there's your plus would be up here in this area. And down here would be my minus. Now, if I take a series of measurements, like in this case, 3 hours, I average them, I do standard deviation, I'm going to hit the instrument spec. As a land surveyor, it's good to know how this works and how to read those specs into your work. So you'll have folks that'll tell you, yeah, I use RTK or more particularly RTN all the time, and I always check in within a couple hundreds. Well, you actually don't. It just so happens you were in the cycle. Let's say I took a shot here, and you can tell over here my northings, 2.45. So let's say I'm at 2.45. Well, I can go through, this is 3 hours of data end to end. Well, at any time right in here, I could take a shot. I'm going to be pretty darn close to 2.45, but I was registering points throughout the day. Understand now, look at my point here. Let's say is, I forgot what it says, 5 minutes in, 6 minutes in, let's say. Let's look at my easting 6 minutes in. Well, I'm at a different scale, but I'm going to say, see if I can get it to come up. Let's zoom in. There's 4 minutes in. It's not the relative scale. It doesn't work. It's still falling. But the point is those aren't always correlated. And so my northing and my easting can be uncorrelated and separating. And what that means to you, most importantly, is you're not relative point to point at any given time. And that's important to understand that how RTK works. Let's look at the elevation. This is better. So if I take a shot at this point, and this is all real data, it's just graphed. Let's see if there it is. So at 13 minutes in, I have a 0.96. Okay, less than a minute later, I have a 0.67. I just dropped 0.3 in less than a minute. So if you're curb staking, you probably can't set 2 curb stakes in a minute, but you don't know where you are in the spectrum. And that's the thing about RTK. So you take or RTN, you take the air and you figure out whether or not your project can absorb it. Because these points over here, let's see what we have at this point. There's a 34 or 41.19, 41.2. That's one of your 5%ers that's outside of your 95%. You think if I'm within 600s at 95%, I must be within 900s all the time. That's not true. Those outliers can be quite a ways out. When you look at the delta in my elevations, what you find is that I have well over half a foot between my min and my max. Let me show you. My elevations in this data set, my minimum and my maximum difference here is, let's see, 0.7. So at any given time, I can have as much as 0.7 between my shots. When I collected this, my unit wasn't moving. I hooked it up to a bipod, braced it, left it to collect for 3 hours, 70 feet from my base. So the air that you see here doesn't have, I wasn't over a point. I wasn't trying to establish a point point, like stake out a coordinate. This is pure measurement at the head of the instrument. And it doesn't have to be level because it's not relative to anything but itself. So an instrument eliminating the other sources of air still produced 7/10 over 3 hours. And you can see that. And in my eastings, or this is my northings, min and max, I have 2/10, 2500ths, which I would expect. And over here, I have 2/10 in my easting. So that's how it works. And that's how you graph it. Eastings, I didn't graph right, but so now here's a 40.64 at 1 hour and 14 minutes in. Here I am at 1 hour and 26 minutes in, and I have a 41.20. You're still working. So I'm not going to say what you can or can't do with RTK, but I can tell you that if you have a regulation or a statute or a certification that you're certifying to, you have vulnerabilities if you're certifying to 500ths, 600ths, ALTA standards, 700ths at 50 parts per million, if you're not measuring long lines. If you're measuring sectionalized land and you have half mile between your quarter corners, you could do an ALTA and hit their spec on that. Because the 50 parts per million, it allows you 50 feet in a million, which means it allows you 500ths in 10,000 in 2 miles. And so the parts per million run up. You'll never hit the 700ths, but the 50 parts per million allows you to measure long lines because it allows for that in the 50 parts per million. So that's RTK accuracy in a nutshell. And if people use it, they certify to it, and they basically get away with it. It's kind of like drunk driving. You can get away with it until you don't. And then when something comes up and you have an issue and they don't have any backup data, they use RTK coordinates, RTN coordinates. Where was your base? And I did a presentation with you guys on expert witness work, not really, but standard of care. Well, this is real easy to bust a surveyor when they sign a certificate, like an ALTA certificate. They don't have any backup data, and I can take a pencil and I can sketch out that you couldn't have that spec. Immediately, you sign something that you actually certified to something that isn't actually true. And so you have a vulnerability there in your practice. I've seen people, if anybody who does heavy construction buildings, we have to certify bolt patterns, and they're generally 1/8 of an inch. They want a 1/16 of an inch, but we as surveyors know that we really can't do 1/16 of an inch. If we use a chain and we use, believe it or not, like a T16, you can get 1/16 into accuracy. If you create redundant networks and what you do where you're doing true line surveying, you can get down to, it's hard to get a 1/16, but you can get down to 100th. I've seen people out using RTK to certify bolt patterns, and with what you just hear, it's impossible to do. Base level instrument is only 300ths, 7 out of 10 measurements. It's 600ths in your northing or in your easting, 9 out of 10. It's the 10th one that kills you. It's not a couple hunds. It could be, if you're here and you hit, got it, you just registered a point that is 3/10 out, 4/10 out. Then you, same data set, you measured here and you say, got the shot. That delta right there is going to cause you a whole lot of problems if you're using this for the wrong application. It's really good for dirt certifications, horizontal and vertical. Normally you can pass through the points, pass through a little bit later to kind of check. It's great for searching coordinates, to look for coordinates. It's fine for long line measurements. But let's think about this. If you need more accuracy, you have the instruments to survey more accurately. Also, if you want relative accuracy, you could RTK a point, 3 points ideally, set up on one, backside another one, have a second backside or foresight check, and you could sit and ray out everything. And now you're relative to yourself. And you'll even find if you set up an instrument and you measure between 2 RTK points that you're going to be off as much as 1/10, or you're going to see this. So you could always hold for the coordinate base to be geographically relative, 1 point bearing to the next point and check to the other point, because you're going to find of the 3, you're probably within 500ths or 700ths. Now you use your instrument and you could ray everything out. Your building, if your entire building, if you were staking out a building, if that building was, depending on what you're doing, relative square to the 100th, but geographically coordinate wise, it was 500ths north, might not matter in most instances, or 700ths northeast. If you're not dealing with setbacks, your large buildings, you could get away with it and your building's good on itself if you're dealing with that kind of thing. But why do it when if you can do static and you can get down to a couple hundredths all day long? Now if you collect data for 5 minutes, you're collecting data, because what people will do, and I'm going to go into the second half of this, is they'll collect data for 5 minutes, 3 minutes, and they let the RTN unit run, and they're registering, and the program is averaging your shots. Well, that doesn't do you any good, because 5 minutes, let's say this shot right here is 21 minutes, let's say, in, and there's 22, and there's 24, and there's 5 minutes right here. 5 minutes of data is producing, if I took one shot here, it's kind of producing something up here, but that same 5 minutes will give you something along here. You see how they're not relative? So what I tell people is, if you're going to collect 5 minutes of data, go ahead and get 7, 8, 9, 10 minutes and post-process the static, because you're only 2 or 3 minutes away from having a good, much better solution. If you're going to take a 5-minute shot, or most nobody does 5 minutes. What I see people doing is they'll do 2 minutes, 3 minutes, or they'll do 180 epochs, which is 3 minutes. There's different ways to set your unit up to collect. The reason you're using RTK or RTN is to save time. You're collecting, if you collect 180 shots, you just wasted 179 seconds, because 3 minutes of data doesn't give you the average of a high and a low. So you're actually working against your point. So if you get out of the truck, you have a good lock on enough units, and the unit is saying it's locked in, you go over to the point, you take one shot, it's no different than taking 60 shots over a minute, because you're not there to create the average over to like here. See how it's all over the place? This from here to here, that's 28 minutes. That's 21. You have 7 minutes of collection to catch the average, which would put you right here. And that's actually not the average of all these shots. You see what I mean? You're averaging, but you don't know where you are in the cycle. It's impossible to know where you are in the cycle. So averaging doesn't help you. And if you're going to average over 5 to 7 minutes, jump to static and pick up good points. That's just some advice I would give you. So when you're doing RTK, RTN, go ahead and get some questions, and we're going to talk about this. I'm just going to show you how to do this in Excel with your own data to check it. Super easy. And like I said, you don't have to take too many notes if you're interested. There's 2 videos recorded on this, but I prefer live as opposed to watching videos. Go ahead, Trent. Any questions? I'm not hearing you, Trent.
I'm not hearing Trent either. It's Rob.
There we go. I had to unmute myself. Does anybody have specific questions kind of on this first part of the conversation that Dave's got? I assume maybe in the second half, you'll kind of go through maybe what you do on a project and kind of go.
Sure.
Okay. Yeah. I was just kind of seeing what your standard of practice would be after seeing all of this data.
Sure.
That was. Then there was a couple of things in the chat following along about the error on how to calculate the error. So, and then Sean says, you cannot accurately shoot road grades with RTK. Been there, done that even with R8 receivers. So calculating the error of the hypotenuse square root of n squared plus e squared, calculate the error. So I don't know if that, John, did that pertain to maybe what Jerry was mentioning earlier? I don't know if you can unmute or maybe type it in the chat, but.
Yes, I was just commenting, when you're showing the differences in northings, I think you have to think about it 3-dimensionally, correct? In terms of northings and eastings, whenever you're talking about error.
Could you say that again, please?
Sorry. Relative to positional error, don't you have to use the hypotenuse? In other words, take into account the northing and easting at any particular episode in time. You were showing examples with northing, but to calculate.
That's exactly right. That's why I was saying it's important to understand that your northing and easting aren't correlated. Your northing could be climbing and your easting could be dropping, and it's that hypotenuse that causes the biggest deltas. That's exactly right.
Yeah, and actually that complicates the 2 sigma error more now, because when you're looking at the 68% error, that's for a single variable. When you talk about bivariate distribution with the north and east, now you're talking error ellipse, and an error ellipse only represents about 38% confidence. So once you start going into 2 and 3 dimensions, that 95% error gets exponentially larger than just a single variable.
So you're saying the specifications on RTK is referring to a single variable?
I'm just saying that we're used to think of things in terms of standard deviation of 1.96 times the standard deviation.
Right.
But as he's demonstrating here, is the northing and the easting are separate. That's a bivariate distribution, which is why we have error ellipses that aren't circular, but are in fact ellipses. And they don't encompass 68% uncertainty. They only encompass about 32% uncertainty. So when you want to get into the 95% uncertainty, it's even larger than a 1.96 multiplier. It depends on your redundancies that you've got built into the network and the number of measurements that you have. It gets very complicated very fast, which is why we have to do all this stuff in software instead of doing it by hand like in the old days.
Thank you.
Nice. Thanks, Jerry. That was awesome.
Yeah. And before we go into how to calculate this yourself, to if you use StarNet or TBC, it does this for you. And if you were to post-process the data and you were to analyze the reports, it'll show you. But what I find is that there's quite a few people out there who don't do adjustments on their data. They're straight coordinates to CAD. And that's not uncommon. It's actually quite common. And so I'm going to use Excel to show you how to calculate this so that you can run your own test. And the truth is if you exceed the spec, you either have a small sample set or you did something wrong, because that instrument spec is optimum coming from the manufacturer. And if you test large data sets, you're going to find that you hit that spec, but you should be able to test it and prove it to yourself or prove it to somebody else, how you did that. And to answer Trent's question, we're like every other survey firm. We mix and match. To answer Trent's question earlier, we're like every survey firm. We mix and match technology. Try it again. We use instruments whenever we need to use instruments. We use static for any work to be done, site work. We are RTK, RTN for searching for points. We use them to collect dirt. We use it to get potholing information, things that fit within those ellipses. And so if we need to be better than that, we do static and we work between our static points. We run everything through StarNet. Our RTK, RTN, we collect coordinates, but most of the time it's from a base station on site. If we're going to use those coordinates for a deliverable to a client, we usually will put up a base and we'll post-process the information to get our coordinates. And the reason is we can process our checks and see what we have, as opposed to an on-site XYZ delta. And a lot of times we mix and match conventional data with RTK and RTN data. And that's why we post-process, is to get that in there. And we see the ellipses up, but that's okay. We know what we have and we use it accordingly. Really, we're still static and conventional if we need to be better than a tenth. As a rule, we kind of use a tenth. We're a little better than a tenth 68% of the time. We're a little better than a tenth. And it's the 5%ers that keep us from using it more for more applications. But that's RTK accuracy. And I welcome any questions that anybody would have on this. But that's how we do it, Trent, is we use that. We still do digital levels. We still do conventional levels. We'll set up a level and level between 2 points so that we get a good vertical difference between those points, so that when we put it in the GPS, we put it into StarNet. I mean, we know the true delta between those vertically, because our GPS gets a little wobbly. And if we're doing a static network in, and then we're doing conventional work between it, and we're applying a geoid as opposed to a benchmark, we get a little wobbly as some of our lines get a little longer. And so we'll run a quick level between some points digitally. We can constrain that to about 100th, and then our project vertical difference is good, even if our elevations are brought in with a geoid. That's kind of how we mix and match.
Got it.
Yeah. RTN is wobbly.
Understood. Go for it, Roberto.
Hey, David. How are you? Can you guys hear me?
We can hear you. Go for it. Yeah, I did.
Hey,
I don't know if
first of all, Thank you so much for hosting this, Trent. These Mentoring Mondays have been great, man. I've been promoting them at school, trying to get everyone in sync with these cool workshops. And the 10-minute surveyor videos, David, those are awesome too. Been promoting those with the students as well. And Rob, you too, man. Thank you so much for supporting our program. David, my question to you is, I guess one of the new things that we're doing at ELAC now is trying to prep students for the FS and the national exam. Not really focusing on the state exam yet, just because I haven't taken that exam yet. I took both the FS and the national. And so my focus is on those two exams. Through your experience and through your, I guess, mentorship with the other LSs, how much of this stuff is in the licensing exam? Because I don't remember seeing too much of this in the FS. But can you comment on what type of problems you would see that would involve this type of topic for the licensing exam? And then my last question to you, David, is what's wrong with clown shoes and dirt bikes? Those 10-minute surveyor videos. I'm like, what is it with these shoes and these bikes? I'll go ahead and turn off my camera, man. I'll leave it up to you now.
Good to see you, Humberto. Of course, we know each other. Yeah, I have a saying, just among my friends, I say, I have seen I'm saying, put away your clown shoes, pack away your mini bikes, meaning let's get serious about this. It's not meant to be derogatory towards our surveys. It's just kind of an inside joke for me that I laugh at. I think it's funny, but it's about 50-50. Some people say you really shouldn't say that, Dave, but I'm not, you're not going to get tested on this enough that it matters. If you're studying for your LS, I mean, it'll be on the test, some version of air analysis, but if you don't understand it, once you're licensed, you're charged in knowing this. If you're surveying to a standard in Nevada, it's important because they actually legislate the accuracy standards. And so whether you're tested on it or not, you are. I'll just show you something here. Let's go to Wacom and I'll make this a little bigger. And Trent will recognize this. This is the Nevada statutes, and you'll see up here positional certainty. And when you go through here, if you look right here, it's 95%. And that means, so when you, and I know that there's people from all over the country on here, but if you look at Nevada and it's 500s at 95%, well, I use 1 second instruments, Trimble S6s. We calibrate them annually. We track our calibrations. We check our tri-brax monthly, so on and so forth. We have a program. We can survey to 500s at 95% routinely. It's a concentrated effort because out of the box, taking your equipment, less air is in there, you can expect to be about 3.5 hundredths at 95% if you create a redundant network. And what do I mean by redundant? Looks like this. Oh, that's not going to do it. Let me find my pen. Here we go. That's a traverse. That's going to be a redundant measurement. If you did a least square of this box here, or you did compass rule, you're going to have the same answer for the most part. It's not going to be much different. But when you do compass rule, what's this? How's that work? How do you get that cross measurement in there? You don't really have a way of doing it. And so like this, that's how you get 3.5 hundredths, is by creating series of triangles through your work where you have redundant measurements. If you start here, back sight here, and you go like straight line traverse, your air ellipses get really big really quick, or running open in. So what we would do is we would set a GPS unit, here, and a GPS unit here. That long line is known within a few hundredths. And so I'm going to adjust those through these points, and it constrains me. And so we just did a survey that's 13,500 feet with, I'm going to say 40 intersections, and it's a long straight line. So we dropped off and did GPS points like every 5th intersection so that we're closing in. And rather than occupy and turn 180s or approximate, there's a couple little curves, we actually put points on the right of way to create a little bit of math. So we put points on the right of way that we GPSed to create a little better math. And we were within that 300ths over, I don't know, tons of setups through the process. And we can repeat that. And we could make this 500ths shown here, but static or conventional only, you're not gonna make that. That static end to end is what brought that air down. So that's kind of telling you what we're doing. Low urban, I'm looking at the Nevada law here, and I can get rid of some of this stuff. There we go. 1500s. I can get low urban with RTK. In Nevada law defines this. I can get there. The longer the lines, the better. But I showed you the math earlier. You're at about 1300ths point to point. But if you were to reflect that back on a precision and say I have 1300ths in a mile, or I have 1300ths in 1300 feet, I go from 1 in 10,000 to, 6 times that, 1 in 40,000. And so RTK would work in a low urban. And then when you look at the precise measurement, of course, that wouldn't work. And then when I look at design surveys, like I'm within 3/10 here, shown here, but I never will touch 300ths. So you should, as a matter of practice, is you should let people know what equipment you used. You don't need to be shy about it. Just say I used RTK or RTN, and then when I follow behind you and I have 1300ths difference between two monuments, I know why. But I think it's a kind of a heads up to let people know your tools. That's it. That was a long answer. If you're studying for the test and you know nothing about error theory, it's something that takes years and a mentor to learn. I probably wouldn't waste my time studying it for the test, but I sure heck wouldn't put a signature on any through it. I know you like to keep these to an hour. I'm going to run through how to check this real quick.
Yeah, no worries. You got time. And then I'll be sure to link.
And to the folks following along, this is all in a video.
Yeah, I was going to say I'll link them afterwards as well. So.
Yeah. Okay, one of the first things I'm going to teach you, and this is on the video, but it's important, is RMS, root mean squared. And root mean squared, you have to understand what that's giving you. It makes you feel really good. You go out and you have your RTK unit set up, and your root mean squared is ticking about 100th, 200ths, and it really makes you feel like you're within 100th or two. I don't think that's an accident, but let me show you how root mean squared works. If I do an average of 10 of them, formula looks like this.
One more time there, Dave. You were just breaking
Okay,
up a little bit.
here's the formula for an average. And I get 10 measurements. Oops. Okay, that's the average of these points. And you'll notice that no one point differs by 100th. So my root mean squared would be divided by 10 because it's a weighted average. So one shot, 0.93, two shots, 0.95, and you can see them count up. So this is the average of those 10 points. Watch what happens here if I change this one by 3/10. Let's say 6. You see how that only changed 400ths? My root mean squared is weighted 9-1. I have 9 measurements that are within 100th. I have one that's 3/10 off. So it's a 9-1 ratio. The more points I get, this thing could be falling and changing by 1/10, 2/10, 3/10, 4/10. My root mean squared won't change. And the reason is it's a weighted average. So root mean squared, all that really tells you is that your instrument is repeating, but the longer you stay there, the more stable it becomes. And if you started in one of those fallings, it's not a measurement of accuracy. And if that thing starts falling 1/10 over, let's say 5 shots, but you've already collected 50, it's 50-5. That won't change your root mean squared even 100th, even though you're in a free fall. And so root mean squared doesn't mean anything if you understand how it works. It just means your instrument is repeating, but the longer you're there, the weight doesn't allow you to see a drastic change in your. So root mean squared is not a security blanket. It doesn't mean anything. It doesn't mean what you want it to mean. It doesn't it makes you feel good, but it's a false indicator as to how that instrument works. And I just showed you in Excel how it works. It changed it 400ths and I changed 3/10. And if on that 10th epic, I hit register, my root mean squared was telling me I'm 100th or 2 or 3. That's why it works that way. So don't rely on it as it's better to get 2 measurements, 3 measurements, root mean squared, because if that's not stable, then it's showing you it's moving around. But the longer you stay there, it won't register large movement because it's weighted 10-1 in this case. So if what you have here is these are 10,000 shots, and I'm going to show you how to do this. Once easting, elevation, averaging. Okay, I showed you how to get an average, and average and mean the same thing to us. There's a variation. You don't care what that is for what we're doing. So by average, all this equals average, and it brings it up. Parenthesis. I grab this and down. Let's try it again. See, I have it will take that entire column of northings, and I have 10,205 northings. Return, and let's go see what I have. That's my average of the shots. And I can do the same for the easting. I'll just show you one more time. Average, oops.
Yeah, I was gonna say, go through it one more time because the first one kind of cut out there. So how you got all selected?
Average. This is for eastings, shift, and down arrow, all at the same time. Oops, didn't catch it. You got to be kind of quick. Shift and down arrow. And it grabs all 200 shots. And because you don't want to sit there with page down, hit return, and that'll give you your average. Now, standard deviation is the difference from your average to your measurement squared. Looks like this. Oops. You're not going to do this longhand. Yeah, you're not going to do longhand, but it's worth showing you something here. Here, just so you get the terms familiar if you're looking to do this. It goes like this. If you measure 100 and the average of measurements is 105, then your residual is 5. Because this is my average of mini measurements. This is my measurement. So if I had a measurement and I had a 110, my average is 105, then my residual here would be -5. And this is a residual. You square these, 5 squared plus 5 squared, square root, and number of measurements 2 minus 1, divide, which is 1. And then you do a square root of that, and you end up with standard deviation. And you don't need to know all that because Excel will do it for you. And normally you have more than 2 measurements, but just so you understand when I say standard deviation, you know what we're talking about. And that's what StarNet and all these other programs do. So standard deviation is right here. So I type in STA, oops, always type equal, STAN, standard, not standardized. I need standard deviation. There we go. So if I go ST, it'll give me a choice, or ST. And this is a sample set here. And these are the same for what we're doing, but I'm going to use A, or S, I'm sorry. So there's my sample set. I go back to my northing, shift and down arrow. I have one extra, I'm not going to worry about that. And let's see what I have. There it is. So there's my standard deviation, 3/100, 1 centimeter out of 10,000 shots, 10,200. I'll show you one more time. Equals STDEV dot S. That's for a set. It gives me a parenthesis, I go shift in down arrow, 10,205 shots, return, and there's my standard deviation. So if you want to know how good your instrument's measuring, put it up in continuous measure in your parking lot, let it run, collect the data, bring it in, 1 second epochs, and bring it into into Excel, and just type in standard, select all the points, and it'll tell you what your standard deviation is. And I'll tell you what it's going to be. It's going to be the instrument spec, unless you do something wrong. It's which can happen because I didn't hit the spec in the vertical. I never went to figure out why, but generally it should be better. So that's how you check your standard deviation. The next thing you're going to want to know is what are my minimums and maximums on that point. So in Excel, you'll see the formula up here. It's called large. And so if I do large, and I'm going to just zoom in because I in respect for people's time here, it's large selection set B2 through B10,205, comma 1, and it will give me the maximum of that entire set. And to the people paying attention, what do you think the small is? Small. And so you would type equals small, parentheses, and you would go over if you have a large selection set, and you would put in shift and down arrow all at the same time. It would grab everything, return, and you would have your min and maxes. And that's how you check your data. And you'll see here that in my min and max, I have 2,500s, and that's northing. Easting, I have 3/10 there, 2,900s, and then I have 7/10. So I went through that earlier. So that's, you don't need to be Mr. Air Theory and I wrote StarNet and whatever. You don't need to be that person. Excel will show you what your equipment is doing as far as a set. Now it's up to you to use it appropriately. What I did just to, and if you don't know how to graph this data, fine. What you do is just take a random 3 minutes, which is 180 seconds. And how you would do that, like in this case, if I highlight this formula, well, there's a lot more than 3 minutes there. But it's 1 second per, 180, 181. So it is. Yeah. So I went from line 2, which is 1 second, to line 181. So there's 3 minutes of data. So you could just go through and grab 3 minutes or 5 minutes at any time. And you could even do a standard deviation on it at any given time to check your data if you're on the same point. So if you want to do continuous measure and bring it in and see what your standard deviation is, there it is. You're not going to see anything in 3 minutes. If you do, you can't report that you exceeded the instrument specifications because you didn't. You just have 3 repeatable data sets. Last thing I'll show you is how to graph this data. I hope people are sticking with me. This is a little wonkish, but I try to make let's say a poor man's error analysis here. So I'm going to do shift and down arrow. Oops, shift in. You have to be kind of quick. Okay, so now I have 10,000 points in my selection set. And I go up here to data. Maybe I don't, formulas. Well, I should have studied this before the class.
I think you're in the right area. I think it's just because you're kind of scrunch down your toolbar on the top there.
Yeah, let me bring it down because I should have a plot. Oh, here you go. Sort. No, it's not sort.
I think it's an insert, Dave.
Oh yeah, insert a graph. There you go.
You're right. You are. Thanks,
insert,
Rob.
Insert charts. There you go.
There you go.
Yep. And then you see insert line or area chart. Nope, it's this one. Okay, insert scatter. There it is. Because we have such a large set, we don't want to do a curve. We take straight lines. So I'm trying to get this to bring up what it is. And there it is. Now you can adjust your scale. You guys can't see it on the screen because it's kind of under the screen, but you can adjust your scale. And what you have here these are my northings to graph, and these are my seconds. And of course, these are actually my measurements and seconds are the same thing in this case. So I have about 10,000 measurements over 3 hours, 2,914 seconds. Let's see. They're at 4,809 seconds. There's my, okay, try it again. Can you hear me now, Trent? Thank you for those signals. So even though this is a blown out scale that I'm showing you, it still shows you the information. It shows you the northings and the eastings, or this is northings, and the timeline. And at this timeline, 5,494 seconds in, there's my northing. I can look at my min and maxes. I can look at my average. And because my average is shown, I can move around my chart and see what my variations are. But it's the same data right here. Let's just look. It's a 2.57 there. And it's a 2.39. So I have 1800s, and I can subtract the seconds convert to minutes, whatever. But that's how you check your data. Now, you don't have to scratch your head, like I said earlier, and say, how did he do that? There's a video on that 10-minute surveyor that shows you all of this. You can back up, forward. The entire other presentation is in there about RTK accuracy. But for those that stuck with me all the way through this, I appreciate it.
Yeah, good stuff, Dave. I'll be sure to link all of that stuff even when I post it on Mentoring Monday's website as well, just so everybody can cross-reference that. And then if you'll send me your PowerPoint, I can kind of throw that in the folder too. But yeah,
I'll send you the PowerPoint.
Yeah, thank you. Go for it, Rob.
George Linsmith put an item in the chat that's exactly what Dave was talking about when he was describing how a D. Woolley and Associates operations run.
Yeah, exactly.
Understanding the tools and using the right tool for the right task. So
absolutely, for sure. Sean, I just threw the link in the chat again, but yes, all of those 10-minute surveys are on YouTube. And like you said, there's 12 of them hosted, and he's already got a couple of them canned that he'll put on later. But any more?
Yeah, they come out every two. Go ahead.
Nope, you're good. Go for it. They come out when?
They come out every 2 weeks, every other Tuesday. And I have one more on sustainability where I go through operating engineers apprenticeship program with some suggestions to better tool them for the profession. And then I go into a least square series where I explain what least squares is and how it works.
Oh, cool.
And so anyway.
Good. Yeah, some good ones to look forward to.
Good job, David. Appreciated it.
Also, thank you. Also, I saw up here a couple of the questions. The essence of us as land surveyors and our licensure is knowing the right tool for the job, because it's what separates us from the carpenters and the plumbers and the grading contractors that use the same equipment. If they use RTN exclusively, plumbers use S6s, carpenters use S6s, S8s, whatever. But what separates you as a licensed professional or would be a licensed professional if you're aspiring is the knowledge of this. And they will never have this knowledge because they're not trained in it. The statutes in some of the states and certainly some of the certifications we sign demands that we understand this and use the right tool. And it's awesome because I just showed you in an hour what separates you from a carpenter, and that creates security for us as professionals. If you're doing what a carpenter does with the same tools, that's a counter argument to the need for licensure and professional status. And so this is actually awesome to know this and to be able to tell a carpenter, I got this. Go ahead and put your equipment away. We're going to get down to 100 today. We're going to get down to 300s. You're playing with fire. And this is good for us. This is good for land surveyors to understand how this equipment works and professional status, because this is the whole core of public protection. And you should, as a land surveyor, be including accuracy statements on your work, whether the law or the ALTA NSPS requires it. You should be putting this on there because it's a hallmark of the professional that separates us from them being deregulation and people moving in. We're probably not going to recapture a lot of the construction like dirt work and things, but that's okay. If you can talk sensibly as to you have a specification that says this needs to be within 300s and your equipment can't do it, they can't prove otherwise, and you can. And now you have honored your professional status with Excel.
And the best part of that is your internet never cut out the whole time on that rant. So I love it. That's awesome. That was good stuff. And it's, yeah, there you go, Roberto. He gave you a heart sign. I love it.
Hey, Trent, you're gone next weekend?
Yeah, but I'm back here for Monday. I'll be back in time for Monday.
I'll be down there Friday, leaving Monday.
Gotcha. Cool. Anybody have any more? That was a great ending point. So I don't know if I want to take another question, but anybody have any more questions that they want to chat about?
Great job.
Yeah, exactly. And just so you know, Dave, you're international at the moment because Peter Cox is on here from Australia.
I should have done it in meters.
No, that's okay. Not so good.
Or upside down.
Well, yeah, exactly.
Yeah.
Well, we do our eastings before our northings as well, so.
There you go. I love it.
Very good. Well, thank you, everybody. And
awesome. Thanks, Dave.
I accept criticisms, and the studio's open to anybody. Or if you want me to do a program on something, I have the ability to take guests in. If I can't offer material, I'll get somebody who can.
Yeah, absolutely. I love it. Thanks, Dave. I appreciate your time.
Have a nice night.
Thanks, David.
Yep.
Thank you, everyone. Take care.